So on page 392 of the packet, we're talking about compound angles. Number 1 is giving us this diagram. And the angle we're looking from point A here. This right here. This is point A up here, C and B. This is the length, the width, and the height. So we are given that the height is 1.5, that the length is 2.7, and the width is 2.0. We are asked to find A, compute the length of the diagonal. In other words, how long is this distance from A to B right there? Well, that length is going to be the square root of 1.5 squared plus 2.7 squared plus 2 squared. Which gives us 3.6796, so 3.680 inches. That's the length. What'd you get? 105. Something went wrong there. You found it? Okay. So next, it asks for the angle CAB. Well, here's CAB, so that's asking for this angle up here. We know, we just found this length here to be the 3.680, and we know this side here is just the height, the 1.5. That right there is the 1.5. And if we're looking for that angle, what we have is the adjacent side and the hypotenuse. Adjacent and hypotenuse make up the cosine. The formula for cosine is that the cosine of an angle equals adjacent over hypotenuse. Well, what do we know here? We know that the adjacent side is 1.5. We know that the hypotenuse is 3.68. We are looking for the angle, which means we're going to have to do an inverse cosine. So second cosine, 1.5 divided by 3.68. Close those parentheses and get 1.1509, so 1.151. And I'm guessing that means my calculator is set in the wrong mode because that doesn't sound right. And there it is. I'm in radian mode, so I got to change it to degrees. So let me try that again. Second cosine, 1.5 divided by 3.68. Ah, shoot. My calculator has been really touchy lately for some reason. Couldn't have anything to do with me being sick and not being quite on top of my game. It has to be the calculator. So that gives me 65.95 degrees. Any questions? Good. Well, this leads us right into our new stuff for today. Which is pretty much what we started talking about yesterday, only we're making it a little bit more specific. We brought up, though, that idea of drilling a hole that goes through at a compound angle. So the hole starts out at this location and comes out on the bottom at this location. So it has been offset in the y direction by a certain amount, which we're going to call W. It's been offset in the x direction by an amount that we're going to call L. And of course, this has to have a thickness to it. Excuse me. It's got to have some sort of a thickness to it, which we're going to label the height, which you can't really see in this diagram. When I place this on the drill press, remember we said if you're looking at the table of the press here, where the press is located here, there's your drill going in. You want the part to be situated such that this hole, the angle of this hole now goes perfectly side to side on the drill press. Now you can tilt the table so that that hole is perfectly up and down as well. So now once you got it rotated the right amount, you can tilt the table so now the hole in the block is perfectly aligned with that vertical drill. So to find that first thing here, which is the angle of rotation right here, R, that's going to be what's used to line up these axes. Well, that angle there is going to be the exact same angle as this angle here. Because these two angles, this one here and this one, have to add up to a right angle. But since this is a square corner, these two also add up to a right angle. And if this angle and this angle, if two angles are complementary to the same angle, they have to be the same. They have to be equal. So what that equates to is, as we were talking yesterday, is in this diagram, if here's our hole, again, just like yesterday, we're concentrating just on this piece now, center to center of hole, as far as our box is going to go. R is this angle. So that angle of rotation, this over here is side W, that right here. This is side L, and this, of course, is the height here, the thickness. W is that. So R, my angle of rotation, is simply the inverse tangent of W over L. The angle of tilt is this one up here. That angle is the inverse tangent, or not inverse tangent, sorry, inverse cosine of H over script L, where script L is the length of the bore. Remember, you find that cursive L is going to be H squared plus capital L squared plus W squared. So as we look at this, let's say that we have let's say that this is 2 inches thick by 1.5 inches wide and a length here of 2 1/4 inches. I want to find R, T, and L. Doesn't really matter which one I find first, but it's probably pretty simple to find R first here off of that triangle. If I draw that right triangle and this is R, what dimensions do I know? Do I know this side? No, I could find it if I wanted to, but I don't need to. Do I know this one? Yeah, it is 1.5. Do I know this one? 2.25. Those are the opposite and the adjacent sides, which tell us we're using a tangent. Definition of tangent is the tangent of an angle is the opposite over the adjacent. So I fill in what I know. Tangent of the angle equals 1.5 over 2.25. Since it's the angle that's missing, that means I have to do an inverse tangent. Which tells us second tangent 1.5 divided by 2.25, close the parentheses, is 33.69 degrees. So that's telling me that if I'm putting this on the table, here's my inlet hole, here's my outlet hole, I'm going to rotate this direction so that this angle now is 33.69 degrees. Next is my angle of tilt. Actually, to find the angle of tilt, it's usually easier if we find L first. Let's find the length of cut. That's going to be the square root of 2 squared plus 1.5 squared plus 2.25 squared, which is 3.363, it looks like. So that's the length of my cut. So then T is going to be formed in this triangle, where here's T. This is still that width of 2.00 inches, or thickness, I should say, of 2.00 inches. And this is L of 3.363 inches. T now, what we have is we have the adjacent and the hypotenuse, which is the cosine. And since we're looking for an angle, I'm just going to jump right to this, that angle T is the inverse cosine of adjacent 2.0 over hypotenuse 3.363. So I do second cosine 2 divided by 3.363 equals 53.51 degrees. So that means if you're looking at that drill press, that table needs to be tilted 53.51 degrees there. Any questions? So let's take this the next step. If we have a drill bit, carbide drill bit going into steel, what's the common cutting speed, surface cutting speed? What's that? Carbide. What is it, about 250? So to 250 feet per minute, right? If we are making a 1/2 inch hole, how many RPM can we turn this? Do you guys remember the formula? C, which is your surface cutting speed, is equal to the diameter of the bit times pi times RPM, right, which we sometimes call N, divided by 12. So what we have here is a 1/2 inch times pi times N over 12, and that has to equal 250. By 12, yep. Now what I would do is I would combine these pieces right here. 1/2 times pi divided by 12. So 0.5 times pi divided by 12 gives me 0.1309, I'm going to call it. So this is 250 equals 0.1309 times N. So to find N now, we have to do what? Divide both sides by 0.1309. Does everybody see where the 0.1309 came from? That's just 1/2 times pi divided by 12. Okay. So 250 divided by 0.1309 is basically 1900 RPM we can run. 1909 RPM. We're going to call it 1900. If your feed rate is drilling through steel, you're looking at probably what, about 2 thousandths per revolution? A little bit more? We'll go 4 thousandths per revolution. How long is it going to take us to cut this? Cutting time. Remember, your cutting time is your feed rate, F. Oops, I got that backwards. It is your length of cut times your feed rate, or over your feed rate, times your RPMs. As long as your length is in inches and your feed rate is in inches, you're okay here, right? Because what this is saying is you're going to go 0.4 inches per revolution, or 0.004 inches per revolution, 1900 revolutions per minute. So when I multiply these two out here, 0.004 times 1900, I get 7.6. What that is telling me is I could go 7.6 inches per minute. Now this length of this cut was 3.36 inches. So I'll put that in, 3.363, right? So I do 3.363 divided by 7.6. And I get 0.4425 minutes. Otherwise known as, if I multiply by 60, about 27 seconds. That's actually, the 4 thousandths is a pretty healthy feed rate going through steel. To make a 3-inch bore, you'd take at least a minute. I would say about 2 thousandths is more of your feed rate on a drill, a 1/2-inch drill. Any questions? This all look familiar? No? This stuff's been a while, hasn't it? The cutting speeds and the feed rates. I'm not going to test you on those again right now, but we do have the end of the semester coming up, so. Almost. What's that? There might be an end of the semester test. Okay, so for homework.
What would you do if you showed up at the last day of class, just all of his assignments or something like that?
Laugh in his face. In the packet, 395 through 397.